Hi, welcome back to es346 Basic Thermodynamics. This is module 7.5, Ideal Gas Entropy Change, and the section in the textbook is section 7.1. Here are the three learning outcomes from this module. At the end, you will understand the two TDS relations for entropy change of ideal gases. You'll be able to calculate the entropy change assuming a constant heat capacity, and you'll also be able to calculate the entropy change assuming a variable heat capacity. So first I want to go ahead and see what we can do with these TDS relations for ideal gases. So first of all, I've written up here the first TDS relationship that we derived in the previous module, and this is true for all materials. We made no assumptions about the material behavior when we derived this equation. But what I'd now like to do is see what form this takes if we assume it's applying just to an ideal gas. And so there's two relations that are important for ideal gases. One is the ideal gas law. This is PV equals RT. That gives me the PVT relationship. And then the other thing is that I know that U is equal to CVT for ideal gases. And so I can go ahead and use that relationship as well. So I'm going to go ahead and plug that into this equation here. So first I'll write this in differential form, which is du is equal to CV dt. And I can plug that in for that du. So I have that ds is equal to CV dt over t. And then for P over T, if I use this ideal gas law, I can see that P over T is equal to R over V. So this becomes R over V dV. And that's actually a pretty important substitution because R is a constant. So now it's really easy to integrate that thing on the right-hand side. So if I want to know the change in entropy now, I need to integrate CV dt over T. And then I can go ahead and integrate this other part now. So this is just going to be R ln of V2 over V1. Now, if CV was constant, so let's say if CV was essentially a constant, I could actually pull it out of the integral in the first one, and I would have this form. Delta S is equal to CV ln of T2 over T1 plus R ln of V2 over V1. So again, remember, these are pretty powerful relationships. I'm able to determine changes in entropy, which we don't have any meters for, using temperature and volume. Two fairly simple things to go ahead and measure. We can get a different form using the second TDS relationship. So remember, the two TDS relationships accomplish the same thing. Some are just a little easier to use than the other. Again, my analogy of like a metric in an English program. So here I'm going to go ahead and use PV equals RT again. And now what I'm going to use is that VH is equal to CP dt, because VH appears in this equation. So let's go ahead and substitute those in and see what form it takes. We get Cp dt over T with the first relationship, and V over T from the ideal gas law, V over T is equal to V over T is R over P. Give me a second there. So this is going to be R over P dP. And now I can go ahead and actually integrate this last term on the right-hand side, because again, R is a constant. So delta S is going to be the integral of Cp dt over T minus, and I can go just integrate this directly. This is going to be R P2 over P1. And again, if Cp is essentially a constant, so that would, for ideal gases, that would be small temperature changes, delta S would be equal to Cp ln of T2 over T1 minus R ln of P2 over P1. I dropped my ln there. It's an ln of P2 over P1. So here's another relationship for determining the entropy. This in terms of temperature and pressure. The first one is in terms of temperature and volume. And which one you use depends on which one is more convenient to you. Let's go ahead and look at what do we do though if we have a variable heat capacity. So if I can't go ahead and just assume Cp is constant and go ahead and pull it out of that integral. Well, what I would need to do is determine, actually do the integration. I'd have to put in some functional form for Cp. So for example, we knew one time we could put in like A plus dt plus Cp squared plus dt cubed. We went through that in a previous module. I could go ahead and put that in there and go ahead and do that integral. It's possible to do. It's just a little bit tedious. However, I want to kind of graphically point out something here. So Cp is only a function of temperature for ideal gases. So Cp over T is just a function of temperature. So if I was to plot, for example, Cp over T as a function of T, I'd see it's got a functional form that looks something like that. Now, this integration is going from my two temperature limits, T1 to T2. So let's say that right there is T1, and this right out here is T2. So the integral that I want is the area underneath that curve between those two dashed lines. And in order to find that area, what I could do is I could just take the area from 0 to T2 and subtract out the area from 0 to T1, and then I would have that integral. And so that's actually kind of nice, because then I could just go ahead and figure out what the values of this integral are once, and then just put them into a table. And so that's something that has been done, and it's given the symbol S with a little degree symbol up here like this, and it is simply defined as the integral from 0 to some temperature of Cp over T dt. Right? This is called the standard state entropy. And what it represents is the temperature contribution to entropy. So just go ahead and looking at changes in temperature. In fact, if you look at this TdS relationship, this is the temperature contribution, and there's the pressure contribution to entropy. And what we're doing is we're determining just the temperature contribution there. So this is this symbol over here, this superscript 0 means that it happens at one pressure, or 1 atmosphere pressure, and then we can account for different pressures with that term. So that's why it's called the standard state entropy. If I go ahead and put that into this equation here, I have delta S is equal to, and now it's just going to be S20 minus S10. So the value of my standard state entropy at my two temperatures minus R ln of P2 over P1. So I'm going to just kind of add incrementally my temperature contribution and my pressure contribution. Now, these values here, you only have to do these once, and in fact, somebody else has already done them for us. And so, if you look at, for example, table A17, which is ideal gas properties of air, on the far left-hand column, we have temperature. If you look on the far right-hand column, there is S0. That's the standard state entropy. The units, this is in English, is kilojoules per kilogram Kelvin, the same as entropy. So this is the temperature contribution of entropy as a function of temperature. So you can go ahead and just look up any particular temperature and look up your particular value of S superscript 0, and you could put those together for the temperature part. Right? This is table A17. This is air, and so recall that S0 was the integral of Cp over T dt. Cp is different for all different materials, so this table only applies to air. And in your book, actually, there's a whole series of tables, A17 to A25, for different gases. So there's our air, oxygen, nitrogen, carbon dioxide, carbon monoxide, various other ones. And so depending on what material you do, you would pick out which appropriate table you want to go ahead and get your standard state entropies from. So before we do an example, I want to kind of put some context to it about why we might actually care about it. And so one of the things that comes up I wanted to talk about here is a turbocharger that you might have in a car, particularly people that like to soup up their cars. And the way a turbocharger works, the point of it is, if you want to get more power out of your engine, if you were to put more air in, you can go ahead and put more fuel in as well, and you can get more power with each individual stroke. So what you want to do is you want to pressurize the intake air. And one way to pressurize the intake air is to go ahead and take your engine exhaust, have that spin on a turbine that is connected with a direct rod up to a compressor, and they'll go ahead and compress the intake air. So as you're driving, the exhaust goes ahead and compresses the intake air, and that's the way the turbo works. And it's another reason why turbos only work once the engine is actually running. You can't start with the turbo on, but once it's running, it works. So the point is, I'm going to go ahead and compress the air that's going into the intake cylinder. Now, most of the intake air is exactly just air. There's a little bit of fuel in there, but it's so small that I can go ahead and assume that the whole mixture is just an ideal gas. Here's a picture of what a supercharger looks like. This is out of a Ford Mustang, apparently. And so this is the supercharger right here. You have the intake air coming in, and it's getting compressed right before it's put into the engine. So let's go ahead and do a problem with a turbocharger. So imagine we have a turbocharger, and we measure the intake to the turbocharger, and we find out it's coming in at 32 degrees Fahrenheit, and it doesn't have any pressure, so 0 psi gauge. And then it goes ahead and pressurizes it to 20 psi gauge, but the temperature goes up to 250. So my intake over here is 32 Fahrenheit, and I'll write this in absolutes. This is going to be 14.7 psia. And then the outtake is going to be 250 degrees Fahrenheit, and it's at 20 psi G, so that's going to be 34.7 psi A. So I've got two inlet conditions and two outlet conditions of pressure and temperature, and those are independent. So I can go ahead and determine what my change in entropy is using those values there. So this is 250 degrees. It's not necessarily real large. Let's go ahead and just assume that Cp is a constant for now. And so we can go ahead and say that delta S is equal to Cp ln of T2 over T1 minus R ln of P2 over P1. Right? So let's go ahead and put our values in there. We can just do that directly now. So Cp of air is about 0.24, and that's BTUs per pound mass R. And then the natural log of my temperature, and so this is going to be T2, which is 250. I need to go ahead and add 460 to that, so it's going to be 710 over 492. That needs to be in degrees Rankine. And then I'm going to do minus an R in English units of 0.06855 to make those units the same, which will be BTUs per pound mass R. And then the natural log of final pressure, which is 34.7 over 14.7. And we can go ahead and just do that arithmetic there. And delta S is 0.0292. That is BTUs per pound mass R. So that's the change in entropy as I go through the turbocharger. Now, there's a couple things I want to point out here. This term right over here was positive. The temperature went up. That was a positive contribution to the entropy. But here, I'm subtracting this value here. And so this is the log of a number greater than 1. I'm subtracting it. So that actually gives me a negative contribution. So when I look at the change in entropy, there's a positive contribution from increasing the temperature, but a negative contribution from increasing the pressure. And we saw in a previous module why that is with entropy, that increasing the pressure goes ahead and decreases the total, or decreases the entropy for that contribution. Now I see that the total entropy here, though, is positive. And again, for anything that actually exists in the universe, the best you can do is have 0, or I'm going to have some positive value. And what this represents here is irreversibilities in my turbocharger. And you might wonder, well, what is that from? Well, it could be due to friction, if it's not perfectly oiled. And it also could be due to turbulence. So when people design things like turbochargers, they design it so that there's a minimum of turbulence. And turbulence you could think of as a type of fluid friction. And so the best that my turbocharger could ever be is that this term completely balances this term and I have a change in entropy of 0. If someone told you they built a turbocharger and the entropy actually decreased through it, you should go ahead and tell them to go take a hike. All right. We looked at something where we assumed that the heat capacity was constant, and I want to talk now about a situation where that's not a good assumption to make. And here what I'm showing, this is actually a jet burner. So what we have with the fuel gases coming in that are then getting ignited and then exhausted out of this jet engine. And inside these, temperature changes can be thousands of degrees. And when you're doing energy balances over these and determining how efficient they are, it's important to calculate what the entropy changes are of the gases, both the gases being burned and then the gases that are just getting moved through. And for example, nitrogen, a lot of nitrogen goes through. In fact, it's 79% of all air. So a lot of nitrogen comes in, doesn't get involved with the combustion process, but gets heated up, and so it has a large increase in entropy. And you'll see later in later chapters of the book it's important to be able to quantify that. So this is a case where you have large enough temperature changes we need to account for it. So let's go ahead and do an example with that. We're just going to look at the nitrogen contribution in this, and the nitrogen is going to come in at 25 degrees Celsius, and then it's going to exit at 1,000 degrees Celsius. And I want to know what's the change in entropy. And this is going to be in a more or less constant pressure combustor. So if I'm going to go ahead and calculate what my entropy change is here, delta S is, and now I'm not going to assume a constant heat capacity. And so what I need to do is integrate Cp over T dt minus R ln of P2 over P1. And it's a constant pressure combustor, so that term right there is going to go ahead and be 0. The log of 1 is 0, so that term is 0. And this becomes simply S20 minus S10. S10. So I'm going to go ahead and now what I'm going to do is just look up these values on the table. So we have 1,000 degrees Celsius at the exit, and that is 1273 Kelvin. And then the inlet is 25 degrees Celsius, which is 298 Kelvin. Okay, and the reason I did that is we're going to get these values for the standard state entropy off of, here I'm going to go to table A18 because we're dealing with nitrogen. So these are ideal gas properties of nitrogen. And the table is in values of degrees Kelvin. So the first one we can get is at 298 Kelvin. So 298 Kelvin is right here. And if I look over, my standard state entropy value is 191.502. And note up here, the units are kilojoules per kilomole Kelvin, not kilogram like it is for air, slightly different. And we'll address that here in a minute. And our other temperature that we had was 1273, so it was in between these two values right here. We were 1273, so we need to interpolate a value between those two. And I did that interpolation, and that number is 236.114. So there's going to be my value of standard state entropy at 1273. The other one that I'll use is 191.502. All right, so let's come back here, and we're finding our standard state entropy. And since our units were in per kilomole, I'm going to put a solid bar over there to tell me that those units are slightly different. And so now the difference between that is this 236.114 minus 191.502. And if I do that arithmetic, it is 44.612. And the units are kilojoules per kilomole Kelvin. And if you want to convert that per kilogram, we'll go ahead and use the molecular weight. And so 1 kilomole, and for nitrogen, the molecular weight of that is 28.013. That is kilograms per kilomole. And you can actually get those molecular weight values off of table A1. And then that comes out to be 1.593. And the units are kilojoules per kilogram Kelvin.